Okay, 2.2, here's my take. We have a say on number 1 here. Circle of radius 5, length of the arc that subtends a central angle of 224 degrees is. And so here's what I'm thinking about that. You know, here's the circle they're talking about. Radius 5, we draw the idea in, you know, at least get a picture in your head. Radius is 5, subtends a central angle of 224 degrees. So they have this arc. There's a central angle, means it goes through the center here. Like a piece of pie or pizza or something, 224 degrees. That's a giant one. So it's going to be more than 180, you know, by about 45 degrees, 44 degrees more than 180, whatever. It's a big angle, you know. You don't have to draw it well, but it's a pretty big angle, 200 something degrees. Anyway, so it's all this, but then they're asking you, what is the length of the arc that subtends that angle? And so that's most of the way around the circle. And so again, my take on this, guys, is just to say, well, if I had to figure out the length of most of the way around the circle, I'm going to start by finding the distance around the whole circle and then timesing by what fraction of it we've taken up. And that'll work in degrees or radians or any other units you want to use. So distance around the whole circle is what we call the circumference. And so you guys might remember the circumference is, if I can figure out the distance across it, that's the diameter. So this is 5, so the diameter is 10 or something, you know, 5 and 5 more. The diameter is 10, then I'll just times that by pi, because pi number of distance across will be the circumference. And so what I would do is exactly that, the distance around it. They call it the circumference. I'm just going to draw a little circle or a little arrow around to signify that's what this part stands for, the distance around the whole circle. That's going to be 10 in this case times pi, because it's 5 and another 5 makes 10 times pi. So 10 pi is how far it is, 10 pi units or 10 pi steps around. You can picture that as being 10 times 3.14 be about 31 and a half steps around. And then I'll times that by however much fraction I'm using up. In this case, they give it to us in degrees. So we're using 224 degrees. Degrees of the whole circle all the way around would be 360. So I'm looking at 224 degrees out of 360. And then once you got that, use your calculator just to times it all, you know, remember, use the pi button, and then you have 10 pi over 1 times 224 out of 360. You can reduce it if you want, or else just times it and then get a decimal. You know, 224 times 10 would be 2,240 times pi, and then over 1 times 360 is 360. And again, you can reduce it if you like, but it doesn't really matter because you're going to put it in a calculator and then round it off to the hundredths place anyway. That's my take on that one. Same thing works in radians. Oh, I'm still annotating. Same thing works in radians. You just say, I'm going to figure out the distance around the whole circle, and then I'll times it by whatever fraction I'm using up. So on question number 2 here, we would handle it in the same way, just remembering that radians are not out of 360, they're out of 2 pi for the whole distance around. So if I had this one on number 2, we have radius is 4 miles, boom, okay, 4. And then the central angle is 2 radians. They don't do it in terms of pi, they're just saying it's 2 radians. Pi number of radians is all the way across, so that's about 3 radians, you know, so we're looking at about 2/3 of the way around there, or 2/3 of the way across half, whatever. It's some kind of a big angle, but it's not way huge. It's obtuse though. Anyway, again, you can draw it right, or you can draw it way not to scale, whatever. 2 radians, here we are, you know. And so we're wondering, what is the length of the arc that goes from here to there? Well, the length of the arc is a fraction of the whole distance around. So we do that same thing. We're going to say, it's here in blue, 4, and then 4 more across will be 8 times that by pi. Then, hold on. Oh, yeah. And then we have 2 radians is that the arc's worth that we're using up. So that's 2 radians out of a full distance around them. It's not 360 in radians, it's 2 pi's worth. And so we're just kind of done, and we times it, you know, put 8 pi over 1 times this fraction straight across. Again, you can reduce things all you like. The 2's are canceling, the pi's are canceling. Looks like we don't even need a fraction or a calculator on this one because everything canceled out. This is just 8 over 1 times 1. So we're looking at just 8 miles, you know. Seems to be, and I'm sure they did that on purpose, but anyway, I got a nice clean answer on that one. On the next deal, let's see. Okay, on the next deal, hey, I just opened up something. I didn't, oh my goodness. Okay, we're good. Okay. Oh yeah, Earth travels around. Okay. So then here's the thing. They're saying, okay, the orbit of the Earth is 93 million miles. Find the distance that the Earth travels in one day in this path around the sun. Remember, they're saying assume a 365-day year. Don't worry about any like part of a year, to add up to an eventual leap year kind of a thing. Let's simplify it to 365 days. So check this out. If we were to say, okay, here's the sun, and then here's, the Earth is orbiting around it and all this stuff. This is not drawn to scale, obviously. And so here, since we're not to scale, we'll go ahead and simplify the idea. We're saying here's the middle of the sun, and then the radius of the orbit is what we're really looking at here anyway. So this might be like the sun itself, but a radius of our orbit is regardless of how big that sun is, 93 million miles. And so I'm going to put 93M here, stand for million, or you could put MIL or whatever else you want to put to remind yourself. Anyway, but then we have 1 day's worth. And so that's interesting because 1 year is, of course, a full travel around. So we're saying a full year is 365 of these. Notice this is not in terms of degrees, nor is it in terms of radians. This is in terms of days. So what we could do is simply say, well, I'll just do the usual thing and say if it's 93 million, then double that across. We'll figure out the distance around the whole thing, and we'll times it by what fraction we're taking up. Well, we're only doing 1 day out of a whole year's worth of days. So the fraction will be 1 out of 365. Don't even worry about degrees or about radians or any of that is what I would do. This is just my take on it. And then what's 93 times 2? That would be 186, I guess. So now you have 186 million miles. They put the millions in the answer, so you don't have to put all the zeros in there because they're just going to say million after it. So I wouldn't bother to put the zeros for the millions. Anyway, so now we have 186 million as all the way across the diameter, times that by pi to get the distance around the whole thing. Here we go. And then times it by 1 day out of 300, excuse me. Okay, so whatever I was saying, 1 over 365, times that like crazy, use a calculator, and you got yourself an answer. That's 186 pi times 1, whatever, out of 1 times 365. There's our top and bottom, and I would just shoot it in a calculator. You might even get away with just writing this fraction in there as long as you have the pi on there. But let's see here, boom, 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 boom. They say round to 1 decimal place, so probably go ahead and shoot it in a calculator and then round it to the 10th place, like they say, is probably what they're looking for. Okay, let's see here. Next one is a little bit weirder. Oh yeah, I mean to clear this up. Okay. So next one, we have to find a distance along an arc along the surface of the Earth. And so here's the Earth this time. This is not the orbit of the Earth. This is the blue planet itself. And so now we're looking around the surface of the Earth, and they say, this time they give us a weird angle, and they do put it in sort of in degrees, but it's actually in a fraction of a degree. They say it's an angle on the, okay, find a distance along an arc. That's what we're doing again. That subtends, and dig this, a central angle of 4 minutes, and so then they define what they mean by that. And in this context, minutes means it's a 60th of a degree. It's a part of a degree. And so what we'll say about that, and if you're wondering, do they do seconds as well? And indeed they do. Seconds are a 60th of a minute, as you're used to. Anyway, and so that means for us, we could picture this and just say like it's a tiny angle. This is way more than 4 minutes, but I can't draw it small enough for that. So I'm just going to say it's a small angle, and then we'll just claim that it's 4 minutes, And so let's see here what else they give us. So 4 minutes, what they're saying is that's 4 minutes. Well, each minute is a 60th of a degree. So this is 4/60ths of a degree is the number of degrees of that angle here, which actually incidentally is the number of degrees that we define for the arc, if you want to say it that way. Anyway, so that's 4/60ths of a degree. It's not even 1 degree. It's like a 15th of a degree if you reduce that. And then the radius that we're given is 3960. That's 3,960, almost 4,000 miles radius. which means almost 8,000 miles diameter. So here we go, like we do, you know, and just doing the same old thing. We're going to say 3960, 2 of that, whatever that is, you know, times that by pi. Pretend like I did 2 times 3960 there. And then I'll say, well, okay, let's go ahead and run those numbers. I'll pause it for a second while I run the numbers. Okay, ran the numbers. Turns out it's easy enough to times by 2 if you think it through. But anyway, so this ends up being twice of that across. Another 3960 across gives us 7,920. Oh my goodness, 7,920, whatever it is. Anyway, times that by pi, of course. And there's the distance around the whole thing, like we say. And now we're just going to times it by this tiny little fraction that we're actually using. So then we're using a part of a degree. So really, in a way, it's out of a full 360 degrees still. So that's what we'll put this as part of, you know? All right, so then we're talking 460. It's of a degree. It's not even a whole degree, but it's still degrees out of 360. It's some part of a degree, you know, part of a degree out of 360 degrees. That's a little weird, but whatever. Or you can figure out how many minutes it is to go around the whole thing, and that would be fine too. That would be like a bunch, you know, and maybe it'd be easier that way. But I'll show you what my take on this. This is a part of a degree out of 360 degrees. And then there's any number of ways to simplify this. Well, a quick take would be, remember, well, here's our 7920 pi, so don't forget about that. That's the distance around the whole thing, and you can over 1 that. But then for this fraction, what you might do is, remember, it's a fraction on top of a fraction. If you wanted to put 360 over 1, then that's the bottom fraction, and this is the top fraction. And so if I were to think of this over that, what we're looking at is 4, here, I'll put it over here, 4 out of 60 divided by 360 over 1. But you know how to divide fractions. That's going to be 4 out of 60 times by 1 over 360. So again, and of course, you'd get the same computation if you did want to consider how many minutes were in a full road, I would say revolution is what I would call this. Anyway, that being the case, oh no, this would be a rotation, I guess. Well, whatever. Anyway, we have 4 times 1 in that way. So that's easy enough on the top. And then whatever 60 times 360 is, I think it's 21600 or something like that, times 360. And then we'll just times it, and get yourself an answer by the time you're done with that. So that looks good. Let's clear that all off. And then the next topic that comes up is, okay. Very similar, and you can handle it very similarly. We have the area of a sector, and that's what these next few things are talking about. And then I'll probably just do one of these things because it translates well once we get the idea. Whether you're doing in radians or degrees or whatever else, if they do something weird, they're all the same approach, and it's almost identical to the approach we were just taking with the arc length. And so, check this out. Hold on a second. Okay, so well, we could do it in green, I guess. So we have a circle. They give us a radius of 3.1 on number 5 here. I have a radius 3.1. Pretend my circle looked better. Here we'll do a little bit more circly. Well, it's not any better. 3.1 radius. And then an angle of 5 degrees. That's a tiny little angle. I'll just make it kind of a small angle. This is more than 5 degrees for sure. But whatever, it's a small angle. And then what they're asking us for this time, though, is what's the area of the sector? Meaning, like, how much area is this pizza pie here, you know, or piece of pie, rather, or looks more like watermelon with the colors I chose. But say we're flat, you know, and we're doing 2-dimensional circle area here. How much area are we talking about here? How much cheese are we putting on top of the pizza? And that's going to be a square footage thing, or square inches, or square units, you know. And so one thing we have to remember about this, it's same strategy, but we're just talking area here. So we're going to get area of the whole circle, you know. I'll put circle area, and then we'll times it by, once again, whatever fraction we're using. It's the same thing as before, but instead of the distance around being the circumference, we call it, now we're talking about trying to find the area of the whole circle. And so how much square footage is there in the whole circle? And then times that by how many, you know, degrees or whatever that we're using, you know, out of the whole thing. And so you might remember, maybe not, that the area of a circle, and again, this is not obvious. There's reasons why we do it this way, but I can show you that on the side if you like. We have the area of a circle, you might remember, is the radius times itself times pi, or pi r squared. A lot of people say, pi r squared. Anyway, and so that's the area of a circle thing. And so we'll say 3.1 times itself times pi, times that like crazy, put it over 1 if you want it to be a fraction. And then we'll say, well, we have angle of 5 degrees. That's 5 out of 360. And we're just running numbers from there. And so you can write it out longhand if you like, or not. This is over 1. And then we have pi times 3.1 times itself is a b times another 3.1. And then times that by 5 over 360. If you want everything to look like fractions, you could just put all this over 1. And then it's just times it, times it, times it, times it, times it. And then the bottom that you divide by is 360, because that's what 1 times 360 is. I wouldn't bother to try and reduce stuff much ahead of time, because we're going to be doing calculator stuff anyway. And these decimals are going to work against you in reducing, and so whatever you want to do though. Anyway, that's what happens with this stuff. Same thing with this one. It's going to be the area thing, pi r squared. And then you're just going to say it's the number of radians out of, however many radians there are, remember? And so it's not 360 when we're doing radians, it's 4.2 radians, but out of 2 pi of them, when we're doing radians, it's out of 2 pi. Same idea with this next one here. Let's see what else we got. There, I'll clear the drawings. Okay. All right, tougher ones. Okay, now we got a couple of weird applications here. This next one, we have the area of the region indicated in blue. Whoops, wrong. Okay. The area of the region indicated in blue, meaning like, okay, the area of a sector is the whole piece of pi. It's, going from this angle. Oh, I should not do this in blue. It's going across this little radius and that little radius and the arc, and then coloring in the whole thing. And that's a big old piece of pi, and that's the area of a sector. What they're saying is, don't give me the area of the whole sector. Give me the area of just this funny piece of the sector that's got the arc on it, and then cutting straight across, not worrying about the triangular part of the pizza, or in other words, this is like, if you were to think of it as the ice cream cone and then the ice cream on top, we're just doing the ice cream part. And so what I would suggest, guys, is if we have to figure out the area of the indicated region, we know how to do the area of the whole sector. We know how to do that because we've been doing that. If I could take the whole ice cream cone, or we'll call it a snow cone, that's what it sort of reminds me of right now. We'll take the whole snow cone, and then we'll minus off the cone part, and then what will be left over is exactly what we want. It'll be equal to just the top of, it's just the shaved ice part of the snow cone, it's the actual snow cone part on top. So I take whole thing, whole sector area. This is what we call sector area. This is my take on it anyway. Sector area minus out the triangle area that we don't want, and that'll leave us with the extra, the snow cone leftovers. And so minus out the triangle. I don't know if I need to label triangle when I drew a triangle, but whatever. Triangle area, maybe we'll put that area, equals the leftovers. That's my idea. And we know how to do sector area. So let's do that part real quick, and then we'll talk about the triangle area. We've done that in the past. Let's see here. So if we did sector area, here, let's choose different colors. Okay, sector area, that's going to be like we do. Area of the whole circle times a fraction of it. And so area of the whole circle, here's our radius is 2.4. So that'd be 2.4 times itself, 2.4 squared times pi, and then times by however many degrees we're using up out of the whole 360, where we're using up 107 degrees out of the whole 360, 107 degrees out of 360. That's our whole sector area. And you can run that through a calculator or just save it for later and run it all the numbers at once. There'd be that part of the answer minus this part of the answer, and this will be the triangle part, minus out the triangle area. So what you might remember about triangle area is this. With triangle area, we say it's a base times the height. Now, this is a funny obtuse angle triangle. So really the straight up height would be, what would happen if I extended this 2.4 out further, and then I cut it straight up at a right angle? That could figure out the height for me. And so there's an extra little bit of analysis with these funny kinds of triangles, but it works out well. We'd say this is 2.4. And remember, so this 2.4 is a radius. know, and what's interesting about these radii is that every radius is the same because that's what it means to be a radius, you know, in a circle. And so this part is also 2.4 if we ever need it. And I think that we will. And so to figure out the height of this thing, we could certainly use, secretly, you can use the angle 107. But if we want to view it as a right triangle, we can just say, well, what is this angle? And we could do 180 for like the full 180 minus off the 107, and we'll get what's left over here. And so I'm going to do it that way, but secretly, it's the same sine value or whatever if you just use the 107. And so just, you know, behind the scenes knowledge there, I believe. And so now we got 180 take away 107. That's going to be something, you know. I don't know what that is, 73 degrees or something. Why don't I know this? 80 minus 7 would be 73. Yeah, so we're good. Okay, so then there's 73 degrees is this angle right in there. So if I wanted to figure out, well, what is this part? What is the height of that, you know? Well, we could do right triangle trig and say, here's our angle. And the ratio that I'm looking for is this is the opposite, and that's the 2.4 that I have is the hypotenuse here. This is a hypotenuse in there, that little radius there. So there's a hypotenuse. So opposite over hypotenuse, I put an H. Opposite and hypotenuse, that's going to be sine ratio. And so we say sine of 73 degrees equal to opposite over hypotenuse. So that's over 2.4 times the 2.4 over there, and you got yourself x by itself. So this is sine 73. Make sure you're in degree mode in your calculator. You don't want to be using it in radian mode at this point. And then times 2.4 times that sine 73 by 2.4. And you got yourself a height. And so remember how we take the area of a triangle is it's the base times the height divided by 2 because it's a half of a rectangle or whatever else you want to think of it as. And so then for triangle area now, we'll say it's the base of the triangle. And, you know, I can erase some of this stuff now that we've drawn it all in. Remember, here's our triangle. The base of it is 2.4. There's our base. Times the height is this whole mess, which is 2.4 sine 73. Didn't leave room for that really. Okay, 2.4 sine 73 divided by 2, or you could times it by a half or whatever. And now we have ourselves base times height, half of it. That's the area of the triangle. And now we'll just say area of the whole thing minus the area of the triangle is this minus that equals what's left over. And that's what we want. Shoot all this junk into a calculator. Try and avoid rounding along the way as much as you can. If you don't have a calculator that can handle this whole stinking thing, it's okay to just to do this part and then this part. But I would recommend getting, if you're going to do that, then write down your answers pretty far out there. I would probably say go 6 decimal places out when you're doing this answer and this answer, if you have to do them separate, and just write them out at least 6 decimal places out before you clear the calculator, and then minus your answers that way, and then round it to 3 decimal places at the end. That way you know you're still accurate because you haven't rounded off very much until the very end. Anyway, that's my take on that one. Okay, clear it up. Okay, next deal. A couple other weird applications here. Okay, restaurant at the top of a very tall building in Seattle rotates at 1.05 revolutions every hour. So it's going that fast. Rosa sits to 20.6 meters from the center of the restaurant near a window. And so they have this, you know, it's like this big, oh, now, hey, why is it not clearing? What did I do? Oh, well, who cares? So annotate. Let's choose a color. Okay. What we're seeing here, guys, is this. As she is in some circular thing that's way up high, you know, looking thing in Seattle. And then there's this restaurant, and then she is 20.6 meters from the center of the restaurant. It's like this rotating restaurant, you know? And so then we don't know how far out the whole restaurant circle goes, but we know that she's sitting at 20.6 meters out. So that's how far her seat is. You know, there might be other people sitting further away if it's bigger than that, you know, I don't know. But that's where she is anyway. Anyway, and then they tell us, well, how fast is this thing going? There it's going 1.05 revolutions every hour. So 1 hour goes by and they've gone a little bit over one full revolution. So they've gone one and then just a little bit past that, a 0.05 of a revolution around. That's what we're looking at in the story. And then they start asking us some questions about it. So let's see about that. So there's different ways of approaching this. I'll show you one kind of quick take on it. And, feel free to adjust it as need be. But one thing I'm noticing here, guys, is that if we're looking at rotations is given in units of revolutions per hour, but they're asking you to report them, information in terms of radians and minutes. Well, we might need to start making this or this data speak that language. We'll need to put this stuff into the units that they want to hear it in before we even answer the question, and then it'll be easy enough to answer the question comparatively. And so what I might do is first take down, well, let's see, they're telling me it's 1.05 revolutions per hour. That's how fast this thing is going. That's 1.05 revolutions per each hour. That's not hugely fast or anything, but that's how fast it is, And so what we could do is before we answer the question, we'll just use a trick or do some, if you're good at feeling this out, you might be able to times and divide things until you can tell, what to times and what to divide. And then you'll just know what it's going to be in terms of radians and minutes. But if you have a tough time feeling that out, what a really popular trick is for that is we'll just multiply things by using property of ones, we call it, canceling out units like revolutions here and turning them into radians. And then we'll cancel out hours and turn them into minutes, And of course, you can tell that minutes and hours are related by that's every 1 hour is 60 minutes. And so you might be able to just, once again, feel it out and know what to times where and what to divide where. But if you get that stuff mixed up, an easy way to say it is, here's the rate of spin that we have right now. And I'll put that same rate of spin in other terms by saying, I don't want to have revolutions. I'll cancel the revolutions and replace it with radians. I don't want to have this in terms of per hour. I will cancel the hours out, put an hour on the top, and I will replace the hours with minutes. But you can't just get away with saying things. What we have to do is the reason that we're timesing this, guys, here's the trick. Okay, what do we know about radians and revolutions? There's a relationship here. We know how many radians it takes to get around the whole circle. It's 2 pi of them. So 1 revolution is all the way around a circle. So what we'll say is that 1 revolution is 2 pi radians. And so that way, in a way, if I'm timesing here, I'll just take you off to the side here, 2 pi radians over 1 revolution. Well, these look different, but really they're the same thing. This is the same amount as that. 2 pi radians is the same thing as 1 revolution. So really what we're doing is timesing the same thing on top as we are on the bottom, just like we can always do with fractions, In the olden days, we'd be like, well, you can do whatever you want as long as you do the same thing on top as you do on the bottom. That's what we're doing. It just doesn't look like it. But 2 pi radians is the same thing as 1 revolution. So it works, And then same thing with this. 1 hour is 60 minutes. So I'm going to times by 1 hour over 60 minutes. Oh, those are the same thing. So this is really just timesing the same thing on top as it does on the bottom. But it gives me the units that I want in secret, And so, well, not in secret really, but it was just kind of a undercover approach to get there, or kind of a funny approach. And so we say revolutions canceled out and we have radians, And so that's good. Whatever is on top, the units left over is radians, and that's 1.05 times 2 pi times 1. That's 1.05 times 2 pi, which makes sense because it was 1.05 revolution. I'll times that by 2 pi. That's the number of radians, So you might be able to feel that out. Anyway, and then on the bottom, it was in terms of hours, and now it's minutes. 1 times 1 times 60 is 60, and then the units left over is minutes. So now what we have is the same info they gave us. They said it's 1.05 revolutions every hour. We're saying that's whatever 1.05 times 2 pi is, that's how many radians we go through every minute, And so a radian is, of course, about that much, because this is a radius, and so radian is a radius's worth of rotation. That's how far we're going in in this case, it's every 60 minutes. So it's still an hour. but at least it's in terms of minutes, you know? And so this ends up giving us the same information. If we times this all out, it's going to be over 2 pi radians every 60 minutes, you know? But whatever. What's cool about this, guys, is now we can answer the question. They're saying, through how many radians does Rosa turn in 112 minutes? There's a lot of ways to do this. What I might recommend is just divide this stuff up and say 1.05 times 2 pi divided by 60. And what that will give you is some number of radians per minute. You know, if you divide that number by 60, it will give you however many radians you're going through per minute, you know, and that'll tell us our radians per minute speed. I'm going to pause this while I run that number. What it looks like that came out to is in radians per minute, if I do this times that, times pi button, you know, divide by 60 or whatever, we're getting into 0.1 something radians per minute, but I'm not going to round it off real well here. I mean, do whatever they ask you to. This says 2 decimal places, so that should be good enough. In this case, it's 0.11 with my numbers. If you feel like going more accurate than that to use it on the next place, that's fine, but I'm getting 0.11 because it's 0.109, etc. Anyway, and so 0.11 radians per minute is what we're looking at here. And then their second question is, how far does Rosa move in 112 minutes? You know, we know how many radians. Something went funny here. Oh, I didn't answer the question. Just don't mind me. Okay, this is the number of radians per minute, but I had to answer how many radians does she go in 112 minutes. So I'm not going to round off my 0.11 yet. We're telling, okay, so the speed she's going at, sorry, I paused the recording and lost myself. So we have 0.1099557, you know, we'll just stop it at 557. That's pretty stinking far out. Radians per minute. That's how fast she's going. And again, if you don't want to use the decimal, what I actually oftentimes do is I'll just keep this number here uncleared in the calculator. So it's really the whole problem still. And then I'm going to do something with the 112 minutes and I'll just use the number that's uncleared on the calculator to do it. That's what I'd recommend. So leave this thing, you know, I put ... because it's longer than that. Go ahead and use the whole the whole stinking thing that's still on the calculator, or leave it as a whole math problem if you don't want to hit enter or equals yet. And then, well, if we're saying if this is how many radians that Rosa goes through every minute, well, and then in 112 minutes, she's going to do 112 times as many of those. So then we'll just say, so that times by, you know, that times by 112. Whoops, that's supposed to say 112. Anyway, so that answer that we just got, that whole whatever 0.1 thing, the 1.05 times 2 pi divided by 60 became some mess. Take that times 112 minutes worth, because that's how fast she was going every minute. Now, or how far she was going, how many radians she was going every minute, and then 112 minutes worth of that. Well, let's see what we got. Times by 112. We're looking at 12.315. And then there's more, of course, but 12.32 radians, pretty stinking accurate there. And then they're saying, how far does she go in 112 minutes? They were saying before, how many radians does she go? Now they're asking how far, meaning they want to know how many meters. You know, radians are kind of vague if you don't define them well, if you're not thinking about how big the radius was. But now if we want to put it into common linear units that, you know, people are used to, well, you know, that are consistent, because radians are big and then they're small and stuff. What we can do is we'll say, well, how big is the radius, you know? And so we're doing 12.23 radians every 112 minutes. So in that 112 minutes, well, we're doing 12 point, here, I'll put different color. In that same 112 minutes, we've done 12.32 radians worth. But how big is a radian? Well, a radian is 20.6 meters. So we'll say 20.6 meters worth for every radian times 12 point something radians worth. We'll just times them and get ourselves an answer. That's how I would take care of that problem. Okay, and then the last one, clear it off. Okay. Next one, number 10. What we got here, guys, annotate. Car speedometer is geared accurately to give your speed using a certain tire size, meaning if we have 14-inch diameter wheels, which is just the wheel part, the metal, and then a tire that's an extra 4.25 or 4.25, inches worth of tire, then if we put those together, what we have is the full circle that that your car is accounted for, the speedometer. So this were the wheel part. What they're saying is this is the first 14 inches, and then an extra 4 inches goes around it. There's the tire part, right? Looking good, Adam. And so then that's an extra 4.25 inches there. If they're going to ask us to figure out stuff, what they're really talking about is they're saying your car's instruments are properly calibrated. Say, how many times should your tire rotate per second if you're traveling at 40 miles per hour? That's something worth figuring out. But what is sort of to set the stage here is, remember, they're saying the car is geared and sorry, I'm looking for verbs here. Is programmed, we'll say, because everything's computerized now, to give you speed based on how big is the actual radius of your tire going around. But that'll be the radius of the wheel plus the radius of the tire together makes one big radius of the functioning tire, And so this is 14 inches and then another 4.25. So really the radius that they're considering here is not either of those numbers. It's you plus them together. 14 plus 4. That's the big radius that we're looking at, is 18.25 for, both of those put together to be one big radius of your actual tire radius, Okay. So assuming that you have the 4.25s on there and that you didn't get some, other wild tires on there, and you didn't switch out the wheels for different size rims or anything weird, then this thing can accurately predict your speed based on how fast your tires are spinning here. Okay. So they're saying, well, okay, how many times should your tire rotate per second? So how many revolutions per second is sort of what they're asking for. How many times should your tire rotate per second? I'm going to call that revolutions per second. Or you can call it rotations if you want to. But anyway, if you're traveling at 40 miles an hour, and what I'm seeing here is just like the last problem, we're seeing different units being used. They're giving you miles per hour to work with, and you have to turn them into revolutions per second, And so let's see if we can make that work. Let's start with 40 miles. I'm going to put MI for miles per hour. And if that's per hour, that means for every 1 hour. So I'll put a little 1 there. And we're going to do some timesing and canceling until we can turn that into what we want, which is in this case, revolutions per second, And I don't know how many of these fractions we're going to need. So I'll just put a bunch and whatever we need. If we're talking about per second, I don't want hours in there. And so that'll be the easier one to get rid of. So let's turn hours into minutes, or you could go hours into seconds directly because there's 3,600 of them if you know that. But otherwise, just say hours, turn that into minutes. 1 hour is 60 minutes. Cancel the hours. Now we got minutes on the bottom. And then we'll be like, well, I don't want minutes really. I want seconds. So I'll cancel that. I'll cancel the minutes and put seconds on the bottom. And we know that 1 minute is the same as 60 seconds. So now we got something per hour is the same thing as per what looks like 3,600 seconds, or 60 times 60 seconds. Well, whatever. Don't worry about the numbers for now. We're just saying, well, we got it in terms of seconds now. And then miles, I have to somehow turn that thing into our revolutions here. And so that'll be interesting. Let's see what kind of units we're dealing with. We're talking revolutions here. The only information we're given so far is diameter that's in inches here. And so that's what this little double quotation looks like. These quote marks, that means inches. And so I can do miles into inches probably. And then if we wanted to turn our inches into revolutions, then that'll work too. So I'm going to change colors for the second part of this. That was the time part. Now we're talking about the distance part with the miles. Let's cancel miles. And I know that I could do miles to feet pretty directly because 1 mile is 5,280 feet. I happen to remember that. Feel free to look that up if you don't remember it, but it's 5,280 feet. The miles that way are canceled. And then we could say, well, I don't want feet. the closest I'm to get is inches directly, and then I'll turn that into revolutions probably. And so I don't want feet. I'll turn it into inches here. And once I get inches, I think I can work with it. Let's see here. Feet will cancel. We know that 12 inches makes 1 foot. And then from there, let's see if we can turn those inches into revolutions. And so let's see if I can get the inches to cancel out. Then we'll get revolutions. I'll put revs up here on the top. If we can figure out a relationship between those, and we might have to actually do a second one or whatever. Let's see here. Yeah, here I'll show you a cheater's way. We'll just go from inches to radians maybe, and then we'll turn those radians to revolutions because we see how big a radius is. That's 18.5 inches. So we have a relationship between inches and radians. That's what I might do. And then radians we can turn into revolutions. And this is a huge long string of conversions, you know? And that's why it's convenient to do it this way when you have complicated problems, is you don't have to think about every little bit about, well, what is it that I'm timesing it? What am I dividing, you know? It can be done the other way, and there's benefit to doing it the other way if you can, you know, make yourself get that. But this is a very convenient and consistently good method, you know? And so, okay, what do we know about inches to revolutions? I didn't want to do directly. We could probably figure that out, but inches to radians I can do is we'll say, well, for every 1 radian is, you know, 1 radius is worth. So that's 18 something inches, 18.25 inches. Okay, inches are out. Now I just want the radians out, and then we'll keep the revolutions. And remember what we know about radians and revolutions. That's always the same, is that 1 revolution is 2 pi worth of radians. And so now the radians are canceled, and now I have revolutions on the top for our, whatever we call that unit. Well, it's our distance thing, although revolutions is kind of a funny one. It's angular distance, you know. And then seconds is our time unit now. And I think that's what they're looking for, because they're asking for rotating per second. And so that sort of means, you know, they're talking about a full rotation here. That means for our purposes, that's revolutions per second. I just like to use the word revolutions, but rotations, I mean, you could call it that just as well, because whatever. Anyway, so this is a lot, you know, look at that. I guess well, whatever, in this context, it might be better to call it a rotation. So, okay, here we go, because it's the tire itself we're talking about, not like gum on the tire. That would be revolving around it, you know, who cares? So pretend I put ROT for rotations there, or whatever, or just stick with revolutions. Now, we're at 40 miles per hour. We were given that. We'll translate all that stuff. And now we have this in terms of, what is it? Oh yeah, revolutions or rotations per second. And so they're asking how many per second? Well, by the time I run these numbers, we're answering their first question. They're saying how many times per second? So we'll just go ahead and run these numbers, divide them up, and we'll have rotations or revolutions per second, and it'll be good. So let's see what we got on the top. 40 times 1 times 1 times 5280. So it's 40 times 5280. I'm skipping the ones. Times 12. And then the rest is ones. That's how many revolutions or rotation. I'll go ahead and call it rotations. And then on the bottom, we have 1 times 60 times 60 times 18.25 times 2 pi. So that'll be a lot to keep track of the other way. Although you kind of do it differently mentally, you know, if you do it by another intuitive process, you know. Anyway, so whatever, that's the number of rotations per this many seconds. And so we'll times this all divided by all that, and then we'll call it a day. And what you can do, and if you have a nice enough calculators, oftentimes you can run that all at once and just be like, parentheses, all this, divide sign, parentheses, all this, you know, and that works well. So that's probably what I'll do. Let me pause that for a second so you don't have to wait for me to do that. Okay, and I got your numbers, and I noticed there's a mistake in here that I'm going to have to fix, so I apologize. I said this was 18.25. We're going to have to change that number real quick, but it won't. We don't have to restart the whole problem or anything. That would be unfortunate. Check this out. Annotate. They said this is a 14-inch diameter tire. I don't know why somebody didn't correct me. That means it's a 14-inch diameter all the way across. So the radius of the wheel rather is not a full 14. It's only 7 there, and then plus another 4.25. So wow, sorry about that, guys. Watch out for that. So it's not 14 across. It is 14 across. We need a radius, so that's 7 plus 4.25. So instead of this being 18.25, 7 plus 4 is actually 11.25. And so when we do that, we're going to run that number. This is really an 11.25. Sorry about that. And then let me run those numbers again. Just notice that. Oh, let me actually call this 11.25. See, never happened. All right, interesting, Adam. Okay, numbers again. All right, so ran the right numbers this time. Here we go. Let's see. What was I doing? Oh yeah, annotate this in a different color. We'll put it in pink because there's so much color up there already. What we're looking at here, guys, is then that comes out to, what is it, 9 point, we're looking at 9 point. I guess I could just put this in the answer box. 9 point, and then accurate to 3 decimal places, that is 9.9595. So this is, it would be 959, but then there's another 5 after it that rounds that 9 up. So this is going to be a 6. So it's really more like 9.960 if you want to put it to 3 places out, which is kind of like just 9.96. Whatever. I would put the O just because they asked for 3 places and you never know how they programmed it in. Anyway, so then there's a second part of the problem. And then we're going to use some of the same info here, the same kind of logic, but it becomes, we kind of have to work some of this stuff forward and backwards to answer that part. And so I'm going to clear some of this stuff off. Hold on a second. All right. I didn't mean to actually like erase this part, but it was like 9.960, right? Okay. And that was rotations per second, right? Okay. So that'll work. For the second part, dig this. They said you bought new tires. They're a little bit thicker than the others, not 4.25s, they're 4.85s. And that's fine. But if you don't tell the car that, if you don't have a way to tell the internal computer that, or a way of re-gearing it, if it's like a mechanical system of recalibrating the speedometer, then it's going to give you inaccurate measurements of your speed. And you'll actually, with bigger tires, if they're, imagine if this tire moves once around, well, it goes a little bit far. But if this tire moves once around, it's going way far down the road, So if you have bigger tires, it's actually going to be going further than you think it is in the same amount of time, which means you're going faster. And so this is the situation they're describing. New 4.85-inch tires on those same wheels, and you drive at a constant speed of 55 as far as but then you get pulled over and the claim is that you were speeding, and then what in the world is going on? How far or how fast is the radar saying you're going? Well, since you got bigger tires, you're probably actually going faster than 55 if it says 55. And so keep that in mind. Let's see what we can do about this. Okay, so for starters, this is kind of a two-phase deal. First off, we know you are claiming to have going 50 miles per hour. At least your instrument is claiming that. And so then 55 miles per hour, that means 55 miles in 1 hour. If I want to do like on the last problem, what we could do is real quickly just do a bunch of those conversions until we know how many revolutions or how many rotations that is per second. And then we can refigure all this to say, well, now that I know how many rotations it is per second, how fast is this tire actually spinning? If it's saying 50 miles per hour, if it's saying 55 miles per hour, it's saying that for a reason. And that's because the rotations per second is at a certain speed. So we're going to try and figure out how many rotations per second is your tire going. And then we're going to account for that, saying, well, if it is that many rotations per second, now we'll account for the new actual size of the tires, not the size tires that the computer thinks you have in our first conversion, but your new actual size of tires. And then we'll run those numbers to figure out how many miles per hour it actually is based on the rotations per second with the new tires. And so here we go, guys. We'll say, and I'll give you kind of a quick take on it. Hours becomes, cancel the hours, make it into a minute, cancel the minutes, make it into, not into an hour, into seconds. That'll take care of itself. 1 hour is 60 minutes, 1 minute is 60 seconds. And then miles, we want to turn those into smaller units. So we'll cancel the miles and we'll say 1 mile is a bunch of feet. There's 5,280. And then, there we go. And then 1 foot is 12 inches, and that'll get us into our right units, at least for linear measurements. And that's inches there. But not leaving it in inches, we will say, well, what do we know about inches versus radians here? And that's where things are getting jumbled, right? Because your car is basing this off of 1 radian is, 7 plus 4.25. So it was 11.25 inches per radian, according to the car's computer, and that's where they're getting that 55 from. So this is the old number here still. And then turn those radians into revolutions or into rotations. So then we'll say radians versus rotations here. Well, 1 rotation is always 2 pi radians. So now we have all these numbers and we can run those numbers just like we did on the first part of the problem, same stinking kind of problem, to start with, to figure out the rotations per second here. So let's see here at 55 miles per hour, we got, those same numbers running. That's 55 times, it's basically the same numbers as we ran before. Really, if you wanted to cheat through the problem, you could just do the same thing, but don't use 40, use 55 this time. And so I'm just going to do that. Actually, I still have it on my calculator. Pretend like I wrote all that out. It's 55 times this times that, Anyway, and so then that's going to be, in this case, let me put 55 here in the calculator. Okay. That then becomes more revolutions per second because it's faster than 40 miles per hour, even according to the computer. So it makes sense. Instead of 9.9, we have 13 point something, and so I'm looking at, in this case, that comes out to 13.69439, and so they just want this in the end accurate to a whole number. So I'm just going to give them a few places now, and that'll keep us accurate enough. 13.694 will be plenty enough because, again, at the end, we're going to round to a whole number anyway. So we're looking at 13.694 rotations per second, full rotations per second. And now we'll take those rotations per second, and turn them into miles an hour, kind of backwards this process. And really, there are ways to just kind of flip this all upside down or do it all backwards or something like that. You can do this stuff quick if you do a bunch of these, And so it will be kind of an upside down version of that last process. So now we have 13.694 rotations per second. That's every 1 second. And we'll just kind of do all those backward conversions. Everything here on the bottom will be on the top probably until we get back to miles per hour, And so here we go. Seconds cancels out, and I don't want seconds. I want hours because I want to end up at miles per hour, right? I want to end up with miles per hours, Cancel the seconds, 60 seconds makes a minute. Cancel the minutes out, and then turn that into, not feet there, I was about to write, into hours. And then let's see here, 60 minutes makes an hour. The 60s are on top this time. And then that's good for the time part of it. We're talking hours now. For rotations, I got to turn those into eventually miles. So let's see here, rotations, I can convert those into radians and then into inches and then go up from there. So then rotations to radians, I'll cancel rotations out, so it's starting out with it on the top. So I'll cancel that on the bottom there, turn it into radians. 1 rotation is always 2 pi radians. Again, an upside down of what we had before. And then radians to inches, watch for the changes, because now radians and inches is different from what it was before. We have, in actuality, if you have that many 13 point whatever rotations per second, now we're talking to turn this into actual miles per hour. Well, now we have different tires on there. So that was a 7-inch radius plus another, not 4.25, but now 4.85 inch tire. on there. And so then from there, now we'll say 7 plus 4 is 11. So then that means one radius or one radian is 11.4, no, not 0.4, 11.85 now, not 11.25 like it was before. So 11.85 inches in every radian, pretend like I wrote that there. And then we'll convert those. Now that the radians are out, we'll just go inches out, make them feet, and feet out, make them miles. So here we go. Inches, every 12 inches is 1 foot. That's out. And every, bam, 5,280 feet is 1 mile. We'll run those numbers, 13 point, all this mess times 60 times 1185 divided by the answer of, well, 1 times 1 times 1 times, whatever's on the bottom, 12 and 5,280. And if there's any other numbers, I forgot. Anyway, and that'll give you the number of miles per hour that you actually are going. That's how the cookie bounces. I once again tried to stop the recording and couldn't clear this out. This is embarrassing, or at least one would think it should be anyway. Oh well.